Hello and welcome back to the Apollo AGC restoration. We've only uncovered one fault so far, but it's a big bad one. Our erasable memory module, which you can see here, seems to have a broken wire inside, which does not sound all that bad until you understand how it's constructed inside. This will be easier to follow if you first watch my previous video that explains how core memory works. To make one long story short, it uses small magnetic ferrite rings, one per bit, suspended on thin wires and weaved into a mat. So it should be rather straightforward to do a continuity check of the memory module. You just have to check the continuity of all the addressing wires, 32X and 64Y wires. Then you check every sense wire and every inhibit wire, one for each bit plane, for a total of 16 each. Unfortunately, in the case of the AGC memory module, it's slightly more complicated because it also contains a whole bunch of diodes used to multiplex the address drivers. Also, the sense and inhibit wires are already interconnected in pairs to save some pins. Nevertheless, Mike was able to make a table of what ought to be connected to what, and was patient enough to test every possible wire. And that's how we discovered there was probably a problem with our memory.
We think it has a broken wire inside. We're expecting on every voltage input pin to the memory, we're expecting that pin to be connected to two inhibit lines. And so on this voltage pin, it's connected to the two inhibit lines next to it. And same for this one. But this voltage pin has this inhibit line, but this one is not beeping. Instead of seeing 6 ohms like we see to this inhibit line, we're instead seeing, on the order of tens of mega ohms.
So it's completely open, basically.
Right.
So you confirm that it's still an open.
Still an open.
Yeah. Try it like 10 times just to be sure.
I don't know how many times I've checked that stupid.
So rats, it's really broken. To make matters worse, the memory module is one of the few in our AGC that's entirely potted. Very much like this other potted module, that's how it would look inside. So Mike, can you have a potted module?
Yeah. So
looks black.
It is black, yeah. We can't really see what's going on in here. So luckily, this is one of only a few in here that are potted.
So in order to plan for a repair, my first reaction was to stick it into my company's very expensive X-ray inspection machine, and we cannot thank Samtech enough for helping out. But to know exactly where to look and to understand what we'd see, we'd first need to understand how the module was constructed. The AGC has 2 kilowords of memory, and each word is 16 bits. Today you'd say it has 4 kilobytes of memory. This original drawing shows how cores for one of the 16 bits is stored in a mat of 2048 cores. Usually a bit plane would be assembled in a frame like this, and you would stack as many frames as needed in the final memory. You'd need 16 frames in our case. In the previous video, I showed this IBM core stack, which contains 4 kilobytes, just like the AGC. But the AGC core memory module is way smaller. Obviously, this represented a major advance in memory density. How the hell did they manage to achieve that? The cores used for the AGC memory were actually quite large at 50 mils, so that does not explain why it's so much smaller. However, when it came to make the final memory with 16-bit planes, they simply eschewed the frame system completely. They weave one giant continuous tapestry with all the cores, 32,000 of them. It was subdivided in squares of 16 by 16 cores, separated by small areas of naked wire with no cores. Here is the complete mat for the 16 bits of memory. I could not find pictures of the mat of the block 2 memory, but here is one we believe is from block 1, which was half the capacity. Then they just folded it all up very tightly to make a very small module. We went through the folding diagram and we think that it's folded. Yes, you have it.
Like this.
Can you do a demo? Sure. Where you unfold it, right? And then you fold it.
Fold it.
Right. And that's it. And
then it sits like this.
Right, so that's the long side.
Right.
That's the wide side. So that's what this folding diagram takes us. Actually, we even found some footage of the block 1 mat being folded. Do not blink as the sequence is very short. Again in slow motion.
And we have a failure in bit 16, which are these 8 squares here.
Right. Such failures plagued the development of the AGC memory. This report says there has been a long history of mechanical difficulties in the erasable memory modules. This, by the way, is an excerpt from the 1966 design review, which was done by anti-MIT people and is very critical of the AGC. The problems came mainly from the potting. The issue is that the ferrites were both subject to wide temperature ranges and magnetostrictive, and could not be held in a rigid potting. So in block 1, the folded memory was first potted in a silastic potting and placed in the middle of the module, shown by the dotted lines. The connections to the pins were made, and it was over-potted again up to board 4. Finally, the diodes were put on top, and it was potted a third time with hard epoxy this time. But under thermal and vibration tests, the wires broke at the pins, as shown on the left. To correct the problem, they stress relieved the wires by making a few loose turns, as shown on the right. For early block 2, which is our module, they added a vertical board in between the stack and the pin area, number 6 on the drawing, and used a hard epoxy potting around the pins. But this proves to be even worse. The wires broke at the board interface between the silastic and the hard epoxy coating. However, if it was the case, the breaks would be well outside the core and close to the side of the module, and would stand at least a remote chance of getting to it for a repair. They did eventually find a solution, but even with that, the overly negative report states the module used for flyable computers would not be recommended at this time. Yikes. So when we stuck it in the X-ray, we expected to see the break quite easily. You can see the stack of ferrite cores in the middle, pins on the sides, and diodes across the top. That's the area where I expected the break, right? So you get a small break. This wire is going over here and then comes back here. That's the sideboard, and it goes through it fine, and I swear they had seen the failure in the 1960s, but we don't see any. It's all fine. You can really see the loose turns for the stress relief, but no breaks in the wire. This is probably one of my favorite pictures. It looks like a random jumble of wires, if you ask me. I'm not sure I would have entrusted my life to this computer if I had seen that one. Hello, so today we are at my well-equipped RF lab, well-equipped with old stuff, that is. And we are trying to make a TDR experiment on the Apollo erasable memory module to find out where the break is, while my house is being banged on. And so here the oldie but goodie Tektronix 7854 scope with a TDR head. So right now you can see it's shooting into this lens of coax. So here's the pulse, travels to the end of the coax, and I get a big reflection back because it's an open. Now if I put this short wire, which is basically approximately 50 ohms, going all the way to here, to my probe, which I'm eventually going to put on the memory, then I have added this thing, and if my touchy button allows, hello, there you go, is reflection from this end. And now I'm going to try to probe the pin on which we think the wire is broken. Well, you know, not only we think, but we are absolutely sure of it. So at one point I will touch, and the amount of reflection should diminish. There should be quite a bit still. There you go. So that's not touching, that's touching. And the reason I still have a lot of reflection is because I'm completely mismatched in impedance. So I have a giant impedance mismatch. But it is attached to something compared to when the probe was not touching anything. So let's acquire this one and store it into waveform 3. Store waveform, okay? And now I'm going to move it to the pin next to it, which has a full wire attached to it, we think. Well, we know, because when we test it, it shows continuity. Now I'm going to go down and touch, if I remember which direction is, there you go. So that's not connected, that's connected, and that's the pin that is connected to a normal wire that works. So let's acquire that, there it is, and put it in wavelength memory 4 F wavelengths. Okay, and so now we should see the difference between the one that's connected and one that's disconnected. That's 4. Let's go back to 3. There you go. See that one? See how it moves up? 4 again. So they start the same, and then at one point they diverge, and the one that has a break has more reflectivity to it. So at the point they diverge, that's probably where the break is. And then you see that superimposed, that's the pin that's connected and the pin next to it that has the break. It's definitely consistent with us not seeing a break next to the pin. It's connected to some length of wire. It just changes right here. So fortunately this scope is smarter than it looks, and it can do math. 3 waveform, 4 waveform minus, and it takes a while to calculate, and there we go. And that's basically the two traces are the same, and at this point they diverge. So basically this should tell us how many inches in our break is, and it's not that many. I'm trying a piece of equivalent of just a simple wire to see where I get the same distance for a break, and this is it's a little shorter. So it's 3.2 division, I should be at 3.5. Let me trim another wire. Let's try this. Go back. Bonk. Let's try if that would be about right. I'm getting there. So our wire break is in between this one and that one.
So we just need to put this on the module, and we know the break is right there, or there, or there. Or
yeah, so that's the problem. So now it's a break in the middle. How do we ever know where it is? So we are trying to repeat the same measurement in the frequency domain with an avalanche of HP equipment. So the idea behind this measurement is that if the wire is broken, it should form an antenna and have sharp resonances when the signal wavelength is a submultiple of the wire length. Down here, this little box will allow me to launch a signal and look at the reflection coming back. I'm now trying to probe a good pin where the wire is continuous from one pin to the other through the stack, and we see wigglies, of course, and it starts at 0 and ends up at 600 megahertz. And then if you compare that to the broken wire pin, and you can very clearly see there are some very sharp resonances, and we didn't see that in any of the other similar pins. So whoop, this one at 98 megahertz, this one at 143, and this one at 195 megahertz. Now do we converge on the same length as what we had before. Over here. Flip. Yeah, that's about it. 141, there you go. So here is a wire that seems to give me the same thing. This is how the inhibit wires go, and the sense wires. So inhibit and sense wires have to go through all the cores. So it goes all the way down, then back all the way up. So it snakes around, which makes for actually quite a long distance. We have figured from the side of the core stack and the core themselves, this
About
here
2 centimeters.
is about 20 millimeters. It takes about 20 millimeters to go in, so by the time it's here, it's 140 left, and goes 7 times. 1, 2, 3, 4, 5, 6, 7.
Break. Worst case, that's where the
So
break
the
is.
worst case, the break is smack in the middle. Therefore, we have no chance whatsoever of repairing it. It's just a lost cause.
Could be lesser, and then there's a best case, which is that the wire goes long distance around the outside of the core stack to go in at a different point.
Yeah. So and then we looked at that to say what are our chances, and then we have an X-ray of that thing.
And we can see it come here, but we don't see from that point on. So we just don't know.
We don't
And
know.
It could go around. Unlikely to be 140.
I think it's unlikely. So we do see buses on the top side. On the other side of the thing, there's clearly wires going across, but not on the side where the fault is.
So what would the distance be if it had to go all the way across and then down around to the pin? So we know
go
that's
measure.
about 200.
Yeah, it's too long.
It's too long, right?
Yeah.
Hi everyone, I'm Dag Spicer from the Computer History Museum. The museum actually has several components of the AGC in its permanent collection. So the first thing we have here is actually just a cover from one of the modules. And
this is actually the cover of the module shown in the exhibit, which we'll see later, but it was important to us to see it so we could figure out how to remove it in our own module.
the other module we have here is a complete module. And you can see the pins right there, and I will just leave it here. And this is called an Apollo memory stack module, as you can see from the writing.
Interesting. Yeah.
That is fascinating. I don't know what this is.
Oh, now we're in
it's
trouble.
different!
It's different, yeah. This doesn't match any of our drawings.
Oh wow.
There's no gaps in the pins here.
Oh right.
Like
Right.
there are-
Orange, right. Yeah.
Right away you can see it's an incomplete module, it's missing its diode board on the top. You can also see the white elastic potting going all the way to the pins, so that looks like a block 1, and we could confirm the potting was actually elastic. And Mike just found that this was indeed a block 1.
Yep. So this, the shape of the core stack on the inside and the pattern, or like the groove on the bottom matches pretty closely with this block 1 drawing.
Alright. So could that be a functional module for the block 1?
No, it would need the diodes to be functional. So this is a core stack assembly. So it's one assembly layer down from a complete module.
I see. That's the paperwork that goes with the
This
thing.
is the deed of gift. It's like the paper with his signature on it.
So the guy lives in Massachusetts, so probably got involved in the fabrication of it, would be my guess, right? Was that
Yeah.
Art RCA
For sure.
or Art Raytheon?
Raytheon or something, maybe?
Yeah. They're really, really different mechanically
We have
and
this, do we? I wonder if they relocated the pins from here to there.
Yeah.
The revs
Awesome.
for addressing.
oh, it looks like you're absolutely right.
Yep,
they
same
have a
number.
gap of
Yes.
that's over here, and then there would be those pins that have been
Yeah.
stolen from here and put there.
Yeah.
I would guess for EMI, right, to separate them physically. Mike did probe the block 1 module and confirmed that the inhibit wire broken in ours is meant to have continuity. Sadly, we also confirmed that the cover is also glued on its entire length to the side of the module, so it would be extremely disruptive to remove the cover from our module. So that means it would be glued along the whole side, and yeah, opening it would be destructive.
Yeah.
I think this is yet one other argument against not touching it, right? You can't see it in the X-ray, and then the thing is hard glued.
Is one of the modules on display of use to you? I mean, it would be a really high bar for me to take it off display.
Or we can at least test the pin continuity.
Doesn't it have a saying on it that one bit's not working on that one that's on display?
Right, yeah.
So today we are at the Computer History Museum in the main gallery, where there are some artifacts from the Apollo AGC. And Karen and Chris, maybe you introduce yourself.
Sure, I'm Karen Kroslowitz. I'm the Director of Collections Management.
And Chris?
Hi, I'm Chris. I'm one of the curators here.
Right, and we have just been allowed to carefully take the AGC that was on display off the wall, thanks to Karen and Chris. So thanks very much.
So this is the same module we looked at with Faye, or
Nope.
No.
This is actually a block too.
okay, this is the one you have a ton of pictures of.
Yep.
Okay.
Look at that. Step out of the way.
It's just missing the outer cover, which was never epoxied on.
It's also, like, I think normally there was another layer of potting that enclosed
Okay.
the diode black. This doesn't have.
On this module, you can see the diodes prominently on the top, and also we could confirm that it has the hard black epoxy outer potting used in the early Block 2 modules like ours. So that would be pretty much impossible to remove without major difficulty. One positive news to finish this video is that Mike checked the continuity and it appears to be good. So although I doubt we'll ever get the authorization to use this module in our AGC, we might get a shot at dumping the historical memory content of it once we prove we can get the AGC working with some other memory. So in the meantime, we are already hard at work cooking up plans D and E and F to go around our memory fault. But the frontal attack of just repairing it seems impossible or way too risky at the moment. What do you think? Should we just plug that one right off?
Well, I don't think we can just borrow this one. They might notice it's missing.
Right.